With this, we will start a two-part series of lectures covering the change of bases in explicit form and with examples. Let's recover the axial symmetry example of lectures 9.3 and 9.5. In the latter lecture, we computed the associated matrix with respect of Vj and Vi, where Vj and Vi were purposely chosen in order to form a basis of the domain. This matrix was computed to be the following: 1, 0, 0, negative 1, and V1 belonged to the L-axis, and V2 was perpendicular to V1. We now use the change of bases theorem. For the time being, it will be C of B. It will be nicknamed C of B. Stated in lecture 9.6 to express SL in coordinates. SL in coordinates will be derived by computing the associated matrix with respect of the canonical basis of the domain and the codomain. This has been shown to be equivalent to find the expression in coordinates in the lecture 9.6. By the change of bases theorem, the associated matrix to SL with respect of the canonical basis can be derived from the associated matrix with respect of the bases Vj and Wj. They were the same basis of the domain and the codomain. By means of this formula, we have to multiply on the right by a matrix P and on the left by Q inverse, where P and Q are the change of bases matrices from Vj to Ej and from Wi to Ei. The old basis to the canonical basis. In this case, Vi equals to Wi, so P equals to Q. The first column of P comprises the coefficients of the linear combination expressing the first vector of the new basis in function of the old basis of the domain. P11 is the first coefficient and P21 is the second coefficient of this linear combination. And the second column, the coefficients of the expression of the second vector of the new basis in function always of the old basis. We can compute the whole P at once as follows. Consider the quality of the block matrices. We have on the left-hand side E1, the vector E1, that is 1, 0, and the right-hand side 0, 1. And this equals the block matrix with the column V1 and V2 multiplied on the right-hand side by the matrix P. This equality is equivalent to the equations defining P. That's immediate here from these two expressions. We can derive P from this matrix equality by multiplying by the inverse of this matrix both sides of the equation. Therefore, we get that P equals the inverse of the matrix with the columns V1 and V2 times the identity matrix, because the matrix that has as a column, the first column 1, 0 and the second column 0, 1 is the identity matrix. We have the equality here that P equals the inverse matrix of V1, V2. This yields the following formula. The associated matrix of the axial symmetry around the L-axis with respect of the canonical basis of the domain and codomain equals The associated matrix with respect of Vj and Vi on the domain and codomain, and we know this matrix is 1, 0, 0, negative 1, and we multiply this matrix on the right by P and on the left by Q minus 1. But Q minus 1 equals P minus 1 because P equals to Q, and P is, we derived P from the previous equation, P equals V1 V2 inverse. Therefore, Q minus 1, which is P minus 1, is just V1 V2. Let's call this equality with the star on here, and we will refer to this equality later on in the lecture. We now use this formula in the numerical example that we consider in lecture 9.5. In that example, the line L was generated by the vector 1, 2, and the choice of the clever basis that we made was to let V1 equal to W1 equal to 1, 2, and V2 equal to W2 equal to negative 2, 1, which is an orthogonal vector to 1, 2. Therefore, we have that the associated matrix with respect of the canonical basis of the domain and the codomain is this matrix here, just plugging in the values that we have for the matrices appearing in this formula. So we expand that, and in order to compute P, which is the inverse matrix of this matrix, we use the formula of lecture 8.1, and we end up getting that the inverse is 1 over 5 times 1, 2, negative 2, 1. So the associated matrix with respect of the canonical basis ends up being the following matrix right here. From the associated matrix with respect of the canonical basis, we can immediately derive the expression in coordinates of SL. As we mentioned in the lecture 9.6, we just have to take this matrix and multiply on the right by the generic vector of the domain. In this case, the domain is R2, so the generic vector will have just 2 coordinates. So the SL of x1, x2 is simply the multiplication on the left of the column vector given by x1, x2 by the associated matrix with respect of the canonical basis. We end up with the column vector. We usually write the coordinates form in row with the row vector, the components. Therefore, we take the transpose of this column vector. And what we end up with is this formula. Now, to find the image of any element in the domain, we don't have to solve any equation or any system of linear equations. We just have to plug in the values of the vector we want to find the image of in this expression, and we will immediately get the image. We did have to compute something here before, of course, for determining the matrices P and P inverse, but we do that just once. And then if we have to find the image of 1 million of elements in the domain, we just plug in this expression. We don't have to make any further computation. The formula star can be rewritten in a more explicit form. The formula star refers to the expression that describes the associated matrix of SL with respect of the canonical basis. let alpha be the angle between the line L and the positive x-ray, like in the picture here. We have the x-axis. So if we consider just the positive ray here, then we can define the angle between the line L and this positive x-ray. So let's call alpha this angle. Remember that by construction, alpha is the only angle comprised between the values 0 and pi, and this will be explained in the forthcoming lecture 10.2. Therefore, here I'm just using these definitions, assuming that you already know the definition of angle, that is. Then we can choose V1 to be cos alpha sine alpha, and that will precisely give an element at a distance 1 from the origin on the line L, and V2 an orthogonal vector to it, which can be chosen to be negative sine of alpha comma cosine of alpha. Again, this V2 will be orthogonal to V1 at the distance from the origin 1. The formula star becomes the following equality: associated matrix with respect of the canonical basis of domain and codomain is the associated matrix with respect of the old basis, which is the same as before, multiplied on the right and on the left by the matrix P and Q minus 1. In this case, this is the inverse of the matrix obtained by taking as a column V1, first column, and second column V2. This is the inverse. And this is precisely the matrix with column V1 here and this column V2. If we expand this product of matrices, we derive this expression, which depends just on alpha. So this formula depends, as it should be, just by the angle alpha. Angle alpha determines the axis L. Therefore, that is the only variable that has to be specified in order to write the associated matrix of the axial symmetry. Just like before, the expression of the associated matrix with respect of the canonical basis immediately gives the expression of the homomorphism in coordinates, just multiplying on the right hand side by the generic vector x1, x2 of the domain, and then transposing the result, which is expanded and written down here.